Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 34 and in this lecture we will be studying the effect of mobility on the threshold voltage and other characteristics at cryogenic temperature. So this is the basic outline which we are planning to do in this lecture. We look into scattering mechanism. We will understand what is the meaning of effective mobility and how it varies with temperature as well as with surface electron density. Look at channel mobility versus effective normal field. So, if we vary the transverse direction or even the longitudinal direction electric field, how does it affect the channel mobility? And then look into temperature dependent carrier backscattering mechanisms for this design. Now, this is a very basic fundamental sort of mobility variation for all practical purposes. This is nothing to do with cryogenics. It's actually a very generalized sort of mobility scattering, one graph which actually gives you the full idea about the scattering mechanism. So, on the y axis you have mobility, right, and typically in the log scale because the variation is typically large for mobility, and on the x axis you have temperature. And it is seen that relatively at lower temperatures, as the temperature starts to increase, the mobility actually starts to increase. Therefore, there is a T3 by 2 dependence, which means that, so it is basically T3 by 2 means as with increasing temperature, the mobility starts to increase, right. Then there is a sort of a critical point, turnover point in temperature scale, below which the temperature increases, the mobility starts to decrease. And initially we should understand why this happens, why there is an increase initially and then decreases in mobility, right. It seems therefore that if you want the best sort of mobility, it is always advisable to keep the temperature scale somewhere in this region of operation. But obviously, as you can understand, this is not in your control to do that, especially if you are not working in cryogenics. If you are working in T equals to 300 Kelvin region, which is the room temperature ambient, the temperature is determined by many factors which are extraneous in nature and the user has no control over it, right. It depends upon the environment, it depends upon ambient, it depends upon the processes within the circuit which is happening, which affects the temperature of the circuit itself, and that is the reason it is not there. But let us come to the point why there is an increase in the value of mobility at relatively low temperature. I had also told you in the earlier places that primarily it is scattering mechanism, right. Primarily means when the electrons are moving through a lattice, because it scatters through the lattice points, its velocity falls down and therefore its mobility falls down as you go on increasing the scattering. So, higher the scattering, typically more reduced is the mobility. If there is no scattering, right, which is basically a ballistic transport, then the mobility shoots up extraordinarily high. Let us look at the right hand side first, that is easy to understand, lattice scattering. Say it is something like this. So, the electrons are moving, right, electrons are moving in this direction, let us suppose. I have these lattice points are available. Now, at low temperature, these lattice points will not shift about its mean position, they will be remaining constant, right. So, the electrons can easily pass, the probability of collision with the lattice points are relatively low. However, at higher temperature, if the lattice point starts to vibrate about its own position to a larger extent, then the probability of electron getting scattered by these lattice points are relatively high. That is the reason it is referred to as a lattice scattering here. Therefore, at higher temperature, as the temperature goes on increasing, as the lattice scattering becomes larger and larger, the mobility starts to fall down, and that is the reason you see the mobility is reducing here in this manner. Now, let us concentrate on the reduced temperature. At the reduced temperature, as the temperature goes on increasing, why is the mobility increasing? The mobility is increasing because at this place it is impure scattering dominated mobility which is there. So, as the temperature starts to increase, the electron starts to gain energy more and more, right, and therefore its velocity starts to become larger and the mobility starts to increase. Moreover, at such a low temperature, the impurities which are there, they tend to actually be in spatial domain remain stable, right, and therefore the electron getting scattered with impurity is relatively small, and that is the reason the mobility starts to increase. So, we have two regions of operation. One is lower temperature where mobility is directly proportional to t to the power 3 by 2, and at higher temperature it is t to the power minus 3 by 2. So, that is the reduction which you take place in. Now, this is another plot which I am showing it to you. This is again with temperature only, but mobility on the left hand side. Now, two things to be noted in mind, that as the temperature increases, obviously the mobility actually starts to go down. So, the mobility actually goes down as you move from top to bottom, right. So, this is clear for first thing. Now, as the temperature becomes higher, the electron mobility decreases almost monotonically with increasing surface electron density. This is the surface electron density. What is the surface electron density? Surface electron density primarily meaning that number of inversion charges in the surface at the silicon dioxide interface. As you can see, as the surface charge density increases, the mobility falls down. Why does it fall down? All of you can understand, because as the number of charges become larger, the probability of collision becomes larger, probability of scattering becomes larger, and that is the reason the mobility falls down. However, an interesting point to be noted here is that as the temperature scales down drastically to 15 Kelvin or 37 or 77 Kelvin, the drop is more drastic at higher NS as compared to 300 Kelvin, right. This is simply because at 15 Kelvin your freeze out has taken place, the number of carriers are very small. So, the effective change which you see in the mobility is relatively large, whereas at 300 Kelvin, since the number of carriers are already very high, the effective change is relatively low, right. So, that is a relative position to see between 15 Kelvin and 300 Kelvin. Now, at low temperature, as I have written here, mobility first increases with electron density at low temperature, not at high temperature. At low temperature, if you concentrate typically from 77 to 15 Kelvin, this region, and then rapidly decreases. Quite interesting. The increase is very small increase, does not influence the circuit characteristics to a larger extent, but the drop actually makes it very difficult. So, which means that if you have relatively a larger value of surface electron density, then the mobility falls down. But if you look at the current, the definition of current is basically mu into aspect ratio into charge and all those things. So, though the mobility has fallen down drastically, but you have increased the number of the surface charge density, right. So, since the surface charge, so these two are opposing forces in terms of the drift current which we can extract when you give proper bias to a MOS device. So, this is basically an idea of the variation of effective mobility with temperature. This is again the mobility is plotted as again the log scale versus temperature. Again, the temperature is also in the log scale for various electron densities, surface electron densities. So, number 1 is so as you move from 1 to 2, it is Ns equals to 10 to the power 12, 3 to 10 to the power 12, 5 and 7 to the power 10 to the power 12. And as the value of Ns becomes larger and larger, you can see the mobility starts to go down. Now, above, it has been seen empirically as well as experimentally that mobility is directly proportional to T to the power minus n when you go down to lower temperature higher than 100 Kelvin. Higher than 100, so basically mobility is equal to some constant k to T to the power n, where n is greater than 2. So, let us suppose a T square. So, I get mobility to be inversely proportional to T square, right. Temperature rises by small amount, the mobility falls down drastically by large amount. So, there are two basic sort of boundaries. One is a 100 Kelvin boundary. Now, above 100 Kelvin, as I told you, mobility is inversely proportional to T square. Below 100 Kelvin, mobility strongly depends upon the surface electron density, right. At higher temperature, they all seem to converge together. The variation is relatively small here for the mobility with respect to surface temperature, whereas at low temperature, the variations are typically very large, right. And they are large in the sense that the differences are quite large in that sense. Okay. Now, we will continue, we have already discussed this, but just to underline what we are looking at. At higher temperature, they are dominated by acoustic phonon scattering and also by inter-valley phonon scattering. We will not go into details of this at this stage. You can have a look into many of the standard books. For example, Streetman is there, for example, SMZ is there, Cividis is there, Pierre is there. You can have a look. There are a lot amount of explanation for acoustic phonon and inter-valley. However, just to keep in your mind that higher temperatures, these two scattering mechanisms dominate, and at lower temperature, these two dominate, right. The Coulomb scattering, surface roughness. Coulomb and surface roughness I have already explained to you in our earlier lectures, right. So, and the transition takes place somewhere around 100 to 200 Kelvin, 100 to 150 Kelvin, the transition takes place, right. And it is quite interesting to study the behavior of temperature on the mobility. Now, let us come to the next point. So, All our previous discussion was with the fact that there is no electric field present at any point of time, right. There is no effective electric field. However, in reality you very well know that in a MOS device, for example, there will be always an effective electric field which will depend upon the transverse electric field and the longitudinal electric field. At this stage now, therefore, let us see how does my mobility vary with the effective normal field. Normal field is basically, I have a MOS device, the field is coming from, this is my gate, right. This is the gate, this is oxide, this is metal, gate, oxide and S. So, the electric field, let us suppose in this direction. Then because of the transverse electric field, how does it influence my effective mobility? First understand it physically and then we will look at the numerical aspect which is shown here. As the bias given to the gate side goes on increasing, the electric field goes on increasing, right. As the electric field goes on increasing, they are able to pull the charge carriers closer to the silicon dioxide interface, the electrons. When they are pulled towards the silicon dioxide interface strongly, the scattering mechanisms becomes heavily predominated and therefore the mobility falls down, which means that as you start increasing your gate voltage and you are still below threshold, so say sub threshold, then the number of charge carriers near the silicon dioxide is very small. But as you start increasing the gate voltage and you enter into the deep inversion region, the number of charge carriers increases and they are very close to the interface between silicon dioxide. And therefore, now if you apply an electric field on the drain side, there will be a heavy amount of scattering which will take place on the system, and that will reduce your mobility. So, plotted on the left hand side is there for the mobility with respect to effective electric field. Effective electric field is defined by this formula. Do not worry about all these formulas at this stage, just understand it is directly depending on the value of the gate voltage which we are giving. But what we see is interesting that the mobility falls down drastically, right, because this is understand a log scale here on this case, right. So, it falls down drastically. So, if I take a graph and we see effective mobility on this side, you will see for all practical purposes, it is almost a E square drop, right. So, the mobility is actually inversely proportional to 1 by E square for all of these graph. However, again please keep in mind that the drop at 15 Kelvin is very high as compared to the drop at 300 Kelvin, and this is where the variability study for cryogenics comes into picture, that you have to be very cautious about the fact that at low temperature the sensitivity is very large and therefore you need to model that as well in order to have a stable electronic system. Again, as I discussed with you, the same graph is repeated here. At high temperatures the mobility monotonically decreases with increasing electric field, and at low temperature, as I discussed with you earlier also, the mobility slightly increases. You see this is a small increase here and then it starts to drop down, and this small increase is primarily because at very low temperature, since the interatomic surface scattering is very small, at very low temperature, as the temperature starts to increase, the mobility starts to increase slightly because the velocity of the charge carriers increases in that region and scattering is not predominant. After that point, scattering becomes predominant and the mobility starts to fall down. If you look at the broken line here, as I discussed with you earlier, it gives you an E effective inverse square, which means that it is inversely proportional to the effective square value, and this is primarily attributed to the surface roughness scattering which you see. Now, there are a large number of analytical models of electron mobility already available, right. There are many models which are based on effective electric field on the longitudinal direction. The E effective which we have shown you here are primarily electric fields in the top to bottom direction. However, please also be aware, I do have the graph with me here. Maybe I can show you here. I don't have a graph at this case, but maybe, okay, I will just showcase to you the graph later on, but give you a brief idea what I am trying to say. What I am trying to say is this, that when you lower your dimension of the device and you are scaling down to low dimensions, the electric field in this direction EY not only increases, but the direction in the EX direction also increases. So, the effective electric field in that case becomes equals to EX square plus EY square, and therefore E effective we want to find out is the square root of Ex square plus Ey square, right, and that has to be taken into account when you do a small channel device. So, when you do an analytical model of electron mobility, you need to take into consideration acoustic phonons, intervalley phonons, surface roughness and ionized impurities. The model will also include the concept of effective mass. I hope you know what is the effective mass. We have already discussed in my other lectures also, and overall this thing. Effective mass is primarily to do with, if you remember, the is given by h cut square by d2e dk2, right, and higher the value, lower the mobility. So basically mobility is inversely proportional to m star, right. So in most of the cases you will see that when we do a mobility modeling, the effective mass comes into picture automatically. So therefore that's the reason why, so that the holes have relatively a smaller mobility as compared to electrons, because its effective mass is relatively larger as compared to that of electrons. Now we can do a variation of finding the electronic states through Schrodinger equation and Poisson equation. We will not go into details of that, but most of the cases in classical modeling scheme we use Poisson equation self-consistently with Schrodinger equation in order to get the quantum mechanical picture in the output side. Okay, one important point before we move forward more deep into mobility modeling and temperature dependency is what is known as a relaxation time. What is the meaning of relaxation time is something like this. So, let us suppose the charged particles are getting drifted because of a strong electric field. It scatters by hitting one of the impurity atoms or one of the atoms which is already present there, and it hits at t equals to T1, and then it hits again the next atom at t equals to T2. Then the difference between them, T2 minus T1, is basically the relaxation time. The relaxation time therefore means the time it relaxes before it is being hit by another sort of particle. Higher the relaxation time, lower is the scattering and higher is the mobility, right, and that the average relaxation time, if you see, is given here, energy is given by this particular point. That means tau ion is the relaxation due to impurities, and tau ps is because combined of phonon and surface roughness scattering. The mobility is then defined in terms of tau as this, but this is not how we conventionally define mobility in device physics. We define mobility using Matheson's rules, taking into consideration the mobility, independent mobility of phonon and surface roughness. But if you want to go ahead and try to find the value of mobility through the value of time constants, then this is what you get, right. It is n0 e tau 0, right, me plus nov tau mev upon n0 plus nov. This gives you the effective value of the mobility. We need not go to much details, just for information's sake you should know. So there are two types of phonon. One is thermal phonon, which we already know. You have intervalley phonon and acoustic phonon as well. Phonons are nothing but particles, it's sort of photons, you know. Phonons are just like photons only, but quite different from them. But photon is basically the particle which carries the light from point A to point B. Phonon carries the energy from point A to point B. So you can have acoustic phonons and you can have intervalley phonons as well. On the left hand side, if you see, the mobility is plotted with respect to electric field or combined value of phonon as well as surface roughness, and this gives you I ion. And if you combine this and this, you get the effective mu to be this. It first increases and drops down. This is at 15K, right. At 15K, what we have seen is the phonon and acoustic phonon and surface roughness mobility starts to fall down, whereas the ion implanted mobility starts to rise up, right, and we have discussed the reason for that, and that is the reason why it initially goes up the mobility and then drastically falls down at 15 Kelvin. So if you take surface roughness parameter, then again we have the same plot which I have shown here. This one is basically ionized impurity scattering limited mobility, and at low temperature with increasing, and that is quite interesting, with increasing electric field the mobility actually tends to increase just because of ion impurity scattering. For all other scattering mechanism it actually decreases, for ion scattering it actually increases, and the reason being that when electric field becomes large, the ions which are responsible for scattering mechanism tend to localize itself in energy domain, right, they energize, and in spatial domain also. So the probability of scattering actually goes down, reducing, and therefore the mobility starts to increase. The value of the impurity scattering in this case has been taken to be 8 into 10 to the power 16, and the surface of the parameter has been taken to be 25 into 10 to the power minus 20 meters square. Now Again, continuing with our channel mobility versus effective normalized electric field, as I discussed with you below, this is my 100 Kelvin curve, right? This is my 100 Kelvin curve. So, at low temperature, which is below 100 Kelvin, the electron mobility is limited by the ionized impurity scattering. However, above 100 Kelvin, it is actually limited by the surface roughness scattering here, right? If you look at this graph here, the surface roughness is almost constant independent of temperature here, if you look. But the mobility due to ionic implantation becomes larger, acoustic phonon reduces, your interface trap charges reduces, and mu total is something like this. So, just to keep in your mind, not going to go into details of it, because as a designer, you are at this stage, until and unless you tend to go to master's course or you do want to do a PhD, these phenomena individually you need not study too hard. What you need to study is how mobility varies with temperature, and this is the final total which you see, that it actually drops down at 15 Kelvin as the temperature goes on increasing. This is again I have already discussed with you in the sense. One more thing which you should keep in mind, and this is important, is that as you make your gate voltage higher and higher and you are trying to invert the channel, you do something known as screening effect. What is the meaning of screening effect? Screening effect effectively means that the electric lines of forces, rather than terminating in a particular charge, get screened by maybe a layer of charge particle, right? It may be screened by a layer of charge particle, and therefore the effective electric field which you are actually giving may not be the exact value which is being fed by the electron, right? And that is more so the reason why when we study mobility models, why does it change drastically post inversion, is this is possibly one of the reasons for doing that. Now, let me come to, I will just maybe give you a brief idea before we stop here. Let me come to the temperature dependent carrier backscattering. So, backscattering is that the scattering becomes so large that rather than moving forward, it starts to move backwards in a sense, right? And this happens especially in reduced current in the channel, it happens, and there is a short channel MOSFET effect comes into picture. When you do a modern technology, which is current technology at this stage, then we actually refer to this as ballistic or a quasi-ballistic model into consideration. If you look at the second point of the first heading, that electrons travel from source to drain under the influence of the electric field, let us suppose. Actually, it travels from drain to source because you apply a positive bias at the drain side, let us suppose. Now, when the scatter of phonon impurities or interface roughness, they tend to lose energy, right? And they change direction. And the direction maybe they will be scattered backwards. So, rather than moving forward, they might even get scattered backwards, and that is what is known as backscattering. Why backscattering is important? Because it reduces the current, right? Prevalent in very short channel devices and also in ballistic transport. Carrier backscattering is strongly influences the currents in MOSFET, right? But when you actually apply a very large electric field in the longitudinal direction, backscattering actually goes to 0. We find out from a carrier reflection ratio, which is shown as RSAT, and is related to the mean free path and the critical length. We will not go into details of the backscattering coefficient more than this at this stage, but it depends upon the injection velocity, backscattering coefficient, and the gate overdrive. Now, just to give you two important insight, the critical length is defined in if you look at backscattering near the source channel junction, where the potential drops to approximately kBt. Kb is the Boltzmann's constant, T is the temperature. Now, the problem is that the temperature drops down to cryo, this kBt value goes down. So, your critical length actually goes down. When the critical length actually goes down, this I0 goes down. So, lambda 0 by I0 which you see here, right, this factor actually goes down, right. Now, at short channel lengths, very, very short channel lengths of sub 100 nanometer, the backscattering, it affects the output performance and room temperature. So, these are the backscattering models, again not required for a bachelor's course. You can actually skip these slides, but those who are interested to go ahead and do a deep dive into devices at cryo, this might be of importance to you. There are two components here. So, you see ID sat, the current is given by this formula. What we do, and we insert an extra term here which is B sat, and depends upon the scattering matrix or the scattering parameter here, and depends upon the critical length and the mean free path here, right. And typically, if you look very carefully, higher the value of BD sat, higher will be the value of ID sat. BD sat higher value primarily will only happen when your RSAT, which is the reflection coefficient for backscattering, is relatively low. When this is low, then 1 minus RSAT will be relatively high, and that will make your BSAT go high. So, which means that if I want forward current, I require my BSAT to be as high as possible by reducing the backscattering coefficient. Now, with this we come to the final stages of the lecture, and now this is the one graph which takes care of our every discussion which we have done till now, and this plots mobility versus temperature right from 0 Kelvin to 300 Kelvin, and we have taken from this paper with the sources being mentioned here. And if you do that, interestingly, and this is very interesting, left an example to you, that at very low temperature mobility is directly proportional to temperature in the form of T to the power 0.23. Slightly at higher it becomes linear 1.12. Over that 1.27 does it becomes maximum somewhere around 150 to 200, and that starts to fall down at T equals to minus 0.55, then followed by minus 1.2, and then minus 1.11, and it tends to saturate around 300 Kelvin, right. This is typically 14 nanometer FinFET mobility extraction using the standard models which we have done. With this, let me recapitulate what we did till now. We did a very extensive mobility model variation with temperature, right. And we saw that there are many components of temperature: phonon, surface roughness, and so on and so forth, and its dependency on temperature. How it is dependency on temperature is all about. Sometimes it is impurity limited scattering, other it is basically your lattice scattering limited mobility. Then you also studied backscattering, and then finally we ended up showing you a graph which gives you global sort of mobility variation with respect to applied electric field and temperature, right. So, this was what we have studied in this lecture. I hope you enjoyed it. Until we meet next time, thanks for watching and goodbye.